Ya, assalamualaikum warahmatullahi wabarakatuh. Good afternoon, guys. Let's start ya. As usual, if we wait until let's say 80% or 90%, it is only utopia. It's okay, whatever we have. No, so please don't forget to tick your attendance. Only 23, still have 15. It's quite a lot. Yeah, 15 not yet a tick. It's already almost 10 minutes left. Yeah, from our starting point should be. Then many participant only 27 mean 26. 26 because one in me, yeah. Wow, it's quite quite few. Okay, whatever, yeah. I mean, so okay, I don't mind this. Okay, let's go to our course. As usual, let's recap a bit about what we have uh, last week. Yeah. Okay. Yeah. And check oriented and also algorithm. Okay, yeah. So let's recap about getting started last week. Okay, this yeah. Okay, so about those comments. Yeah. So we discussed last week about uh, what is all about our lecture about the AA. Then, in some sense, we are want to solve the problem, but this problem where it can be calculated. Yeah. For instance, oh, I have a problem that I don't have a girlfriend or boyfriend. Of course, it cannot. This is difficult, but in the sense of technical solution, maybe. Yeah. Anything can be calculated, mean you use computer to solve the problem. And then we have emphasizing about data structure and algorithm, what correctness and efficiency, and in the implementation goal we need robustness, that into robust, not our program, our solution not stop or not being distracted by maybe any noise. And also adaptability, adaptive, can be used for over time, and reusability, that we don't need to start from scratch. Whenever possible, whatever we have, just continue, then can make use from whatever we have. Then we have history, and then what is algorithmic problem and solution. That actual algorithm is only, well, it's not only, it is very big deal, but anyway, anything that you can see the transformation between from input to output. So this is the algorithm, the transformation between input and to output. So this is the algorithm that uh, we try our best, to see uh, what is the pattern, the transformation from input and output. So it is n, so this is fn. The algorithm is the step by step this transformation from this input to output. Then we have example of sorting. It mean we use insertion sort, our playing card. Okay, that we need to emphasize or need to pay attention about correctness here. Yeah, that question we want to sort by ascending, ascending mean from the least to the largest one. Yeah. And then we also learn that the running time depends on number of elements, and then for partially sorted they are an algorithm. Okay, so this is the pseudocode of insertion sort, which we already discussed. And then we also know that we have two approach for designing algorithm, yeah, incremental and DC, divide and conquer. DC, divide and conquer. Incremental is so-called traditional conventional, for instance, iterative looping. But in some sense, for many complicated problem, it can be used if it is kind of simple problem, yes, incremental approach can be. But usually for the sophisticated and more complicated problem, we need to rely on divide and conquer. And one example of this is recursive function, recursive function. Yeah. Okay. And then we want to analyze of algorithm. So it was designing, yeah, the designing. This is kind of designing algorithm here, yeah, incremental, divide and conquer, blah blah blah. So remember we have DAA, design analysis of algorithm. So designing in this, this D, or by the A, analysis of algorithms, DAA, DAA, that is, yeah. So we discuss about efficiency in running time and space use because the only matter in this world that uh, cannot be shrunk, yeah, cannot be shrunk or cannot be folded is only time. The other, yeah, storage it was so expensive. For instance, our hard disk, but now it's become cheaper and cheaper, yeah, because mass production, then space can be sacrificed in order to get increasing in utilized time. Yeah. So this time is the one that cannot be folded. This yes can space. And then efficiency as a function of input size. We learn also that the most important is about the input number. Yeah, can be number of digits, can be numbers of point, yeah, number of data element. Then we also learn about so-called ad hoc algorithm that it is only how to say for particular time, also particular space. Yeah, it is to continuum space and time that maybe this algorithm only can be used in particular time and space. I give you an example, maybe only in this particular time. For instance, it is this 0 o'clock, and this maybe 12 in the lunchtime. Also, again, maybe this is, I say this is also 12 o'clock lunchtime. Also back to the midnight that we pay attention in this particular time, 3. Yeah. In the space, for instance, in here, yeah, particular time that we only need to adjust our algorithm in this particular place, for instance, yeah. Okay. And then the combination of this time and space can be for the ad hoc algorithm. In our political circumstance in Indonesia, we have so many ad hoc committee that once that matter finish and then the committee also been need to be dissolved, need to be dismantled. Yeah? So it's only can be used a matter of time and also a matter of place or the combination of these two. Yeah. Okay. Then we have the RAM model. Yeah. Random access machine model. Okay. And then the thing is for analysis in any algorithm actually we focus on computing running time as a function of input size. Okay, there was an n, yeah, and the time was as t. Then we also learned about best, worst, and average case. That best case, worst case, and average case for particular example. For instance, in this case is insertion sort. Yeah? Insertion sort. Okay. Okay, you got fn for best case and fn square or fn power 2. And average case is fn also power 2. And then in some scenario, actually the average case is usually close to the worst case. Okay, and then when this, in the sense of the diagram, so worst case we call it this is upper bound, and then best case we call it lower bound. And calculating the average case is also very difficult. Yeah? The most easiest is worst case because it often happen. Average case is the most difficult. Oh, no, not most difficult. Difficult, sometimes difficult to calculate. Yeah, this. Okay, so because occurs fairly often, yeah, for the worst case, that's why we focus only to calculate the worst case. Later on, we'll see that we use that big O, and some calculation for big O log n, for instance. Yeah. And as can be seen here, yeah, that average case usually close to the worst case. That's why if it is for the upper bound, it can be said that it is safe to say when we know the worst case, we don't care about average case because we can prevent, yeah, something worse when you know the worst case. Okay. The thing is, for average cases, it can be very difficult. But we know already that average case is close to the worst case, then okay, it is very close, even sometimes the same, yeah, or close to. It's very difficult for the average case. Worst case, fairly often, uh, fairly fairly often occur. Okay, then we focus then worst case. Okay. We know that is often aspect as the worst case for average case. And also, but we learn about the growth function and that anything about log n is the preferable. Yeah, even if you you calculate that log n and it mean you need to multiply by n. It's still okay. Yeah, this comparing to other, even the uh, linear one. Yeah, even the linear one. Okay, and the linear one is this n. Yeah? It's very close here. But usually it's very very little case. It's very small case that we have the linear. Many cases this even worse. You get some power in your function. Yeah? Okay, this is the worst one if anything, and then the power is your input number. This is the worst one because you will get the exponential. Yeah? Exponential. Exponential. In bahasa Indonesia, this sial we pronounce this sial. It means this bad luck. Bad luck is this sial. Call it sial, bad luck. Okay. Okay. So everything about number of input become the power of something. Yeah, can be 2 over n or something. Yeah, this question mark mean any number. Then it is the worst one. Okay. Then when we say, oh, insertion sort, then become the best approach ever. Yeah, because what's that? Fn. Yeah, Fn is the best. Okay. The worst case what? Worst case is Fn over 2. Mean Fn square. Average also Fn square. Okay. So the best is okay with it. Oh, this ever. No, actually when you think other so-called method short, yeah, then you got n log n. Another one is we learn also searching if it is arbitrary input, I mean kind of random, kind of, but of course not random, like arbitrary, yeah, this, then you cannot avoid that for worst case running time is Fn, yeah, then average case is Fn over 2, and then we cannot do better. The lower bound for the problem of searching is an arbitrary sequence, and this is the lower bound. Okay. Then when it is shorted, yeah, I mean the input is shorted, then you can get different approach, and you got better by binary search, yeah, with DC paradigm, but then conquer idea, then you will fold up the time, yeah, you get log n, okay, for the uh, execution, yeah, okay, okay. Let's continue. So this is our recap from last week, okay. Okay, now we want to see the continuation of our lecture. Yeah. Where is 2000? Our DAA. Okay, see its correctness. Okay. This KAA2, yeah, and then KAA3. Yeah. Okay. I have this. Yeah, yeah, this, yeah. Okay, let's check. Make sure it is the same. We check about the same thing. Okay, oh, the same, yeah. Okay. Okay, so this those comment and markup and then those. Okay, so this lecture is about correctness of algorithm, and then growth of function and asymptotic notation. And you guys actually should already pass this mathematics, some basic math revisited. We are not dig deeper, just bit revisited, and then divide and conquer example. The method will, inshallah, will discuss a bit deeper about in here. We mentioned about method, this, and then we want to discuss about, okay. Okay, what is the correctness of algorithm? The algorithm is correct. Correct. You show the truth if for any legal input, it terminates and produces the desired output. And should be legal, because if illegal, I mean, we cannot, we cannot, uh, we cannot, how to say, we cannot say that okay, in any input it will produce the set output. It's only the legal input, because we cannot, you cannot guarantee if it is illegal, then can produce the correct output. So it's okay to say only legal input terminates and produces the desired output only. Yeah, that's correct. The thing is, automatic proof of correctness is not possible. Of course, we want, but it's not possible. It's not possible. Okay. But there are practical techniques and rigorous formalism that help to reason about the correctness of algorithm. Don't worry. We have practical techniques and rigorous formalism to say that any algorithm correct or not. Okay, what is the partial correctness? See, if you have any legal input, then you fit up this to your algorithm, and then you produce the output. Okay. See this. If this point is reached, then this is the desired output. Okay. This partial. I mean, uh, as long as you can produce something. Yeah. We also have another one. Let's see. We also have, still have many not tick. I really don't get it. It's easy to stick. Partial versus total correctness. Partial total correctness. I love to have the picture, but is there any better picture? No, I think this only this. Yeah. So this is like if you have at least one, come here, yeah. Then this is, we call it partial correctness. If this point is reached, then this is the desired output. Yeah. But also can be you have many actually. Yeah, go somewhere. This. Yeah. But for total correctness, this any legal input, and indeed this point reach n, and this desired output. Let me all, all will go here. All will go here. Yeah, can be, because then if then I mean can be there is also opportunity that it is going somewhere, yeah. But here no. Indeed, this point is rich, and this is the desired output n. That means you don't have any alternative to go somewhere. It's called total correctness. But even as can will be seen in our real life, even if even you got this partial correctness, guys, it is really very lucky. How many? All of us. How many? Some of us. That even we don't get any partial correctness in our life, that we never reach this position, this output. Okay. Only total failure or partial failure. Okay. If then, if then, so this and then this. Because maybe you don't reach this, yeah? Maybe you don't reach this, right? But here, for total correctness, you already reach in here. Indeed, this point is reached. It means already done, yeah, yeah. And then, and this is the desired output. So you have no alternative. But of course, in our life and also in DAA, yeah, is not all of our approach can get this total correctness. Our algorithm maybe not get this total correctness. There is also some possibility, yeah, it cannot be reached. But anyway, even we get partial correctness is already worth it. Already worth it. Okay. Assertion. What is assertion? To prove, yeah, even we take what partial correctness, yeah, even only one tiny wire or tiny string, yeah, but our algorithm, we can transform any legal input here, yeah, and pass through algorithm, and then even tiny wine, only one get this, yeah, then we are very lucky because even though only one, we can claim that it is partial correctness happening now. To prove partial correctness, we associate a number of assertions. What is assertion? It is statement. They are statements about the state of the execution, maybe more than one, then, yeah, with specific checkpoint in the algorithm. Okay. So by proving, it means you are need some statements about the state of the execution with specific checkpoints in the algorithm. For instance, this you have. Remember, we also usually array even from the case of playing card. Yeah, you have array of A, right? Then you have array A. It means array with index 1 until array index k form an increasing sequence. This. And this is 1, 3, 5, 7, 12. So you have a specific checkpoint in the algorithm. Okay. So we have assertion, yeah. To prove algorithm, we associate a number of assertion with specific checkpoint in the algorithm. Proof even partial. We don't talk about total correctness. Even partial correctness is enough. When to prove partial correctness is we need to release our effort, and it is quite a lot. I think for total correctness is very difficult, yeah. Even partial is enough. Okay. Then we have this assertion. It means like this A1 until AK. You have specific checkpoint, yeah, in A1, yeah, in A2 until AK. And then we have to pay attention about two conditions in here, yeah, so-called pre and post condition. In pre conditions, what it mentioned, assertion that must be valid before the execution of an algorithm or a subroutine. Precondition and before should be valid first. Post condition, assertion that must be valid after the execution of an algorithm or a subroutine. So you have execution here, yeah, exact. So this state need to be valid. This is valid pre-condition. And after this state should be also valid, right? Post-condition. So the checkpoint is before and after, yeah, for the execution and after the execution. Okay. Another term is called loop invariance. What is invariant? Invariance. It is not variant. Variance. Variant is like many things, many variety of variant. In it means not. Insertion that are valid anytime they are reached. Many times during the execution of an algorithm, for instance, in loops. I mean, if you have 4, of course, this is looping here. So I mean, in every single state here, it should be valid. If one then fail, invalid, I mean error, then we cannot get proof for the partial correctness. Okay. So in any state should be valid anytime. There is no to say there is no change. For instance, this is true. It's like 10 times looping. Yeah. The first one, second until 10, of course, would be true. But even one question false, then it called invariant. Invariant. Okay. It means invalid in any particular time. Then call it variant. Variant. There is a variation in any particular time. So it should be invariant. But if you talk about loops, it means a loop invariant. In any state, it shouldn't be changed. It shouldn't be invalid. So we must show three things about loop invariant. We talk about loop invariant. For initialization, it is true prior to the first iteration. So if say computer in the first state, yeah, 0000, it should be true first. Then you go to the looping. The looping this, I say for. So if it is true prior to the first iteration for initialization, then maintain if it is true before an iteration, it remains true before the next iteration. It's true, yeah. Then okay, you just going into the next iteration, yeah, before the next iteration. So maintain. So here also true. So it state true. It's true. Let's say true. And then okay, first iteration. First. So it remain true. Remain true before even get into the first iteration. And then okay, you got the first iteration. Yeah. And then before go to the second iteration, it also remain true. It's true. And then termination. When loop terminates, the invariant give a useful property to show the correctness of the algorithm. When after terminate here, yeah. So the last one, the terminate, after terminate, then you jump out, right? You jump out. It's also true, still remain true. So the initialization, maintain, and termination need to get what our assertion should be true. Yeah. Okay. Okay. Example of loop invariant. Yeah, for instance, this is what invariant. At the start of each for loop, A1 until J minus 1 consists of elements originally in A1 until J minus 1, but in sorted order. Okay. This is insertion sort, yeah? Yes, it is insertion sort. Insertion sort. Pseudocode, right? So at the start of each for loop, A1 until J minus 1. So this is it at the start for each for loop. So you have this, yeah. So A1 until J minus 1, yeah, because J equal to 2, yeah. So in the beginning mean here, right? In the beginning, before you access everything. Consists of element originally in A1, but in sorted order, yes, right? Because insertion sort and you are in ascending approach. Yeah. So 1, 3, A2, let's say this 5, 7, let's say 10, let's say 12. Yeah. So A1 until J minus 1. J, the first J is 2, right? So it means here, J here. So it means 1, correct, right? Sorted order. And then the second one after the second looping, yeah. Okay. Then here J, 1, 2, less than 5, yeah. This also sorted and so on, right? So it is invariant, consistently true, yeah. In any start of each for loop, you got sorted order in your array A. Array A. Okay. Now initialization, initialization j equal to 2. The invariant trivially hold because A1 is a sorted order. Yes, of course, only one. A1 is only one, of course. One without any comparison, of course, it should be a sorted order, yeah. Like we said, this one because J started from 2, right? So J1, whatever only one, of course, would be sorted, yeah. Okay, now maintain, yeah, this. The inner while loop, this move elements aj minus 1, aj minus 2 until aj minus k 1 position right without changing their order. Then the former aj element is inserted into kth position so that ak1 less than equal to ak less than equal to ak plus 1. aj a1 until j minus 1 sorted, yeah, like before. This is the first case. This sorted, yeah. Okay. Plus aj, then a1 until j sorted. You can imagine this, guys, yeah. We have this, then j, yeah, here, right? Then j minus 1 here, yeah, j minus 1. And then you add up j, yeah, after this while loop here. Of course, should be sorted, yeah. Okay, this is also another one if I put this and I have k in here. So k minus 1, k minus 1 from 1 until k minus 1 is sorted, and then you put k, and then also sorted, right? And then termination. Yeah. The loop terminates when j equal to n plus 1. Yeah, so if I have, what is our example here, yeah? 1, 2, 5, 7, 10, 12 after insertion sort, yeah. And then finish after 12. You have to finish, yeah. You finish after 12, finish, right? So when j equal to n plus 1, right? Then the invariant state A1 until n consists of elements originally in A1 and A1 until n, but in sorted order. It's proof, right? Okay, that you can get this. 1, 2, that 5, 7, 12, yeah. 1, 2, 5, 7, 10, 12, right? Yeah. So it was not sorted, yeah, but now sorted. After that, 4, yeah, after this, you jump out from that. Is the last one. Okay, so that's the proof, yeah, of partial correctness. Okay. Yeah, yeah, partial correctness. Okay, so precondition and then initialization, yeah, yeah, and then maintains and termination. Okay. Then before you have that, you have precon and postcon, preconditions and postcondition before the execution of algorithm. The execution of algorithm. Then we apply our proving in loop invariance by examine, yeah, by examine the initialization, maintains, and termination. Okay, then okay, we'll cut, yeah. Okay, we continue for asymptotic analysis. Okay, what is the goal of asymptotic analysis? Asymptotic, asymptotic analysis we know, yeah. What is asymptotic? Oh, yeah, this. Okay, just any Wikipedia, yeah. Okay, in computer science because in mathematics or computer science, yeah. Asymptotic analysis is also known asymptotic without analysis. Method of describing limiting behavior. Limiting means you are focused only something, yeah. Limit, not all. because our life is too many things, yeah, then need to limit. Okay, it's limit close to zero, limit to plus infinite, and so on. Yeah, we don't particular thing we want to observe. Okay, but remember, yeah, is it asymptotic? There is no asymptomatic. Be careful. Asymptomatic, asymptotic, asystematic. Okay, yeah. Okay. Asymptomatic is about disease, asymptomatic symptom. But this asymptotic, asymptotic, asymptotic analysis. So goal is to simplify analysis. It is the case. Simplify. We need to simplify. Make it simple. Make it humble. Analysis of running time. Running time by getting rid of details. We don't care about too much detail, which may be affected by specific implementation and hardware. This, for instance, programming language should be, I mean, when we say programming should be independent, yeah, but of course in real life also affected by the programming language and the environment. But in a broad, in the broader view, we need to say that this should be independent implementation. That's why we want to get rid if something actually happening and is affected by specific implementation and hardware. Of course, the performance will be affected, yeah, by hardware. It cannot be, we cannot deny of it. But anyway, it is too detailed, and usually people in real would say that the evil is in detail. The evil or the devil is in the detail. Evil or the evil is in the detail. Okay. For instance, this, yeah, like a rounding. If I have 1,000,001, then by hardware, yeah, because we have limitation in um, representing, let's say, any fraction in your float or double. And then, okay, just omit that one and become 1,000,000. Yeah. It doesn't matter. Of course, you actually omit that one, yeah. But see, in the broader view, you see from the highest level, who care about that stupid one, yeah? 1,000,000, 1,000,001 is equal, yeah, similar. We call it similar. Also see, yeah, 3 times n power 2 equal to n power 2. How come 3 is first function if itu, let's say 2, ya, power 2 equal to 4, ya. 3 times 4 equal to 12. Okay. Of course 4 and 12 is different. But you can imagine if the n is so huge, guys, it doesn't matter, yeah. And it's huge, like some tera or exa or 10 times or 10 power 20 or something, it doesn't matter. So we can omit this constant, this constant. Okay. The point is when we get rid the detail, then we will capture the essence. We want to capturing the essence. How the running time of an algorithm increases with the size of the input in the limit. In the limit. We agree, yeah, that from last lecture, yeah, last lecture that it is more important to focus on the input of size, yeah, this, than anything. Because if we say in the broadened view, that's matter. The input size matter. The others, it doesn't matter. Yeah, it doesn't matter. That's why I want to capture the essence by evaluate how the running time is of an algorithm. Any algorithm increases with the size of the input in the limit. Yeah, we focus on the self to input and then in the limit now. Okay. Asymptotically, more efficient algorithms are best for all but small inputs. But sometimes if it is too small input, then it doesn't matter. Any algorithm will be the same. Will be the same output. But if it is the huge number of input, then okay. Any algorithm can be say it is more efficient than others. That's why we want to find a mechanism, yeah, to evaluate whether an algorithm efficient or not comparing to others by the note that input size is very big, huge. Okay, so we want to evaluate the efficiency of any algorithm. Yes. Okay. Okay. They are best for all, but small input. It means we need very big input size. Yeah. If small, maybe 2 or 3, if any algorithm maybe the same. Yeah. But even merge sort become worse comparing to, let's say, insertion sort. Yeah. Because it's small input, but we also realize now that, yeah, live in the big data world. Okay, then matter, yeah, that okay, if that input size is very big, then evaluate or analyze any particular algorithm no matter, yeah, because it can distinguish which one more efficient by the note that it depends of the input size. And if the input size is small, it doesn't matter, everything is the same. But if big data, the input is so big, then okay, we will see which one is more efficient algorithm, yeah, among any uh, bunch or a group of algorithms. Yeah. So now we have so-called big O. It is in English. It's not pronounced like big O, not O. Big O. It's asymptotic notation. We call it big O notation. We already know that worst case is upper bound. Yeah. And then okay, that we make use that our last lecture, yeah, the last week is upper bound B. Okay. By formalization like this, you have Fn equal to big O Gn if there exists constancy and n0 is like a starting point of input size n0 such that Fn less than or equal to C times Gn for n greater than or equal to n0, yeah, the starting point that n become how to say showing, the because as we said before, yeah, this small input but small input. Okay, that's why if small input it does not work here. Yeah, the small input here. That's why we need the initialization, not the initial point, yeah, the input size of n0, then make this function, yeah, okay, no, correct, no, yeah, this efficient. Sorry, not to say efficient, correct, not to say correct, but efficient. This efficient. This, okay. See, yeah, this is still not efficient because the red still greater or how to say higher than that green, yeah, the green line, right? That's why Fn should be less than. Fn should be less than. There is a constancy times Gn for this n greater than or equal to n0. Okay. So Cgn this here. Fn should be less than or equal to. Fn and Gn are function of a non-negative integer. As I said, yeah, the DA always love the fancy term to say positive, they say non-negative. It is positive, right? It's very funny. I say positive. Okay, yeah. And then we use this for worst case analysis. Worst case analysis. So this upper bound, because remember, yeah, this is the up there, okay, going up. Then you have upper bound. You cannot go up anymore. Yeah. So I how to say limit you. I limit you in here. So this is why we call it upper bound for worst case. Worst case, WC, worst case. or UB upper bound. Okay. Bound. Yeah. Okay, so you have limitation in here, yeah. That CGN is like limit you. You cannot how to say always always above you. Yeah. CGN always above you. This is why called upper bound. You always have that limitation in there. Okay. Worst case. Now the one we call the big omega. Yeah, everything from the Greek letter, yeah, Greek symbol, big omega notation. It is similar with big O, but on the opposite direction. Yeah. We call it asymptotic lower bound, LB, lower bound. Fn equal to big omega Gn if there exists constant C and N0 is the same. Yeah. So this is not efficient, yeah, because that CGN is greater than, yeah, Fn, right? CGN greater than Fn. This is why this not efficient, not efficient, not efficient. Okay, this is until this also not efficient. Actually, this is efficient in the sense of uh, Fn, yeah, greater than CGN. Yeah, this is actually okay. Yeah, it is okay. But then when we go here, oh, this is going down. Yeah, so Fn less than CGN. Then until this point, yeah, N0, this N0. Okay, the starting point of input says okay, then Fn always greater than or equal to CGN. Or on the different words say CGN less than or equal to Fn. Okay. So that CGN become the lower bound, yeah, LB. Because Fn always on the top of CGN. So CGN become the always below. Fn always on the top. So CGN always lower than Fn. In this case, CGN always the upper of Fn. Right? Upper of Fn. You are higher than Fn. Here, CGN always lower than Fn. Got it, lower bound, right? Fn always above of CGN. CGN less than or equal to Fn for n greater than or equal to N0. We learned that used to describe best case, PC, best case. And it is lower bound, LB. Remember ya this, yeah? Okay, yeah. Best case, lower bound. Worst case, upper bound. Used to describe best case running time or lower bound of algorithmic problem. For instance, lower bound of searching in an unsorted array. Remember? Unsorted array, like the first. Yeah? Where is that unsorted array? Oh, this. Yeah, this. Yeah. This unsorted array, yeah, like what's the array? Arbitrary. Unsorted array. Unsorted array. Or arbitrary. And kind of random. Yeah? This is unsorted. Yeah? So that's why you cannot beat this. Yeah, the lower bound is big omega n, right? You cannot beat this because you need to traverse one by one, right? This is the only one that you can do one by one because it's unsorted. You cannot beat this. This is the best one. Yeah, the best one. You cannot beat this. This is lower bound, right? You cannot beat it. So the best case is this. Yeah. Okay. Mm-hmm. That like big omega n. Okay, this is the best case. You cannot beat this. You cannot. How come? You cannot. Yeah. Because you need to set one by one, look for one by one, because for unsorted array. Okay. Okay, simple rule how to get rid of the details. Simple rule is drop lower order terms and constant factor. Lower order term delete it, and also constant factor. Yeah. So yeah, 50 n log n is this. Yeah. So which one? Constant 50 ya, delete. Okay, and that's it ya. Pico and log n for the worst case. Worst case, yeah. Worst case is Pico and log n. Because you already delete that 50. Worst case, yeah. It means, of course, you can do better because there is a 50 actually there, but delete it, yeah, delete the 50, you get n log n. Then if you have 7n minus 3, yeah, this constant minus 3, delete it. And you have 7n, and you have constant 7, delete it, yeah, only n. Okay, if 8n power 2 log n plus 5n power 2 plus n, how to do this? Why you got this? Okay. The lower order term, lower order. Okay. Yeah. So you have, yeah, you have n square here. Yeah. Okay, so okay, n first. Yeah, this is the lower. Okay, just delete. Okay. You have also n square, but you multiple by log n. That means you have to delete this also. And then you have also only have 8n power log n. Okay. You have still constant this, yes, 8. Just delete it. You only have to get the to get rid of the detail. You have only n square log n. Then it's correct. Okay. There is a note here that's very interesting. Even though 50 n log n is pico n power 5. 50 n log n. It is expected that such an approximation be of as small an order as possible. Okay. Okay. This of course, yeah, because if you jump this, yeah, go to here, yeah, or if it is uh, you change, yeah, from n log n to n power something, because n over 5. Okay, but we want our approximation make it as smaller as possible in order. Yeah, in order. Okay. And okay, in between we have big theta, yeah, big theta for average, big theta. We call it big theta notation, yeah. We call it tight bond, very tight, not loose, yeah, tight. TB, tight bond. And you can see here, yeah, Fn equal to big theta Gn if there exists constant C1, C2. Of course, we have two because we are in between, yeah, C1 and C2 and N0 starting point of input size such that the Fn what greater than or equal to C1Gn and less than or equal to C2Gn for n greater than or equal to N0. Because you have this, yeah, upper bound and lower bound. So you're tight in between these two functions. You are very tight because there is a limitation. There is how to say there is a boundary, yeah, bound up there and down there, yeah, upper and lower. You are like kind of squeezed, yeah, by these two things. Yeah. You are in between, and you already that this is still wrong. This wrong can oh yeah, until this is correct. So you have n0. Okay. Yeah. Fn equal to p theta gn if only if this Fn equal to big omega gn and also Fn equal to big OGN and also Fn equal to big omega gn. This if it is equal, yeah, if it is equal. I mean, three of them will become alienated. Yeah. Fn and then C1 Gn and also C2 Gn and Gn. So it is like one, or to say like one position. You have Fn equal to big theta Gn if and only if Fn equal to big O Gn and Fn equal to big omega Gn. Big O Fn, the worst case Fn, is often misused instead of big theta Fn. Remember, yeah, average. We already know that usually close to worst one. Yeah, the average case usually close to worst case. And finding average case is very difficult. And that worst case often occurs. Okay, just focus on big O. Okay. That's why usually big O FN if also misuse instead of big data FN because it's difficult to find big data. And then we anytime we just use big O, big O, big O. Actually cannot be there like that. But anyway, that's us. We know the reality in our life that big O, worst case, is occur often, frequently occur. Then best case or average case. Another one is average case very difficult to find. Right? So it is very easy to see when occur frequently. This is so difficult to find. And then we don't care about best case. Okay. Okay, another symptomatic notation, so called little o, two more. Is a little, yeah, little o. We call it non-tied analog of big O. Yeah. For every C, there should exist N0 such that Fn less than, without C, without equal. So there is no equal this, only less than. For N greater than or equal to N0. Used for comparison of running times. If Fn equal to little OGN, it is said that Gn dominates Fn. Back to here, yeah. This here. Because you don't have less than, yeah. Less than, it means you are aligned, yeah, in one line. Because only less than, it means you never touch, yeah, the CGN, right? Right, they call this little o. Gn dominates Fn because Gn for sure always on the top of Fn. Yeah, this. Let's say this, yeah, and let's say this. Okay, never touch. If big O, because there is a equal, yeah, less than equal to equal, so this, and then also can be touched. That Fn can touch that Gn. If little o, never, yeah, never touch Gn. Okay, so non-tied analog of big O. Because non-tied, because never touch means not tied. Yeah. Little omega notation, this little omega, this non-analog, non-tied analog of big omega. It means you have Gn, yeah, 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 yeah. But you never touch, yeah, the Fn never touch Cgn. Yeah. If you have this greater than, yeah, greater than, so Fn greater than or equal to, yeah, Cgn, right? Because you have this equal, yeah. But for little omega, no. So if you have equal, so you can touch CGN. But if little omega, because only have greater than, yeah, then you cannot touch this. This is why we also can say what Fn dominates CGN, yeah. Fn dominates CGN. This, yeah. This is if little o, Gn dominate Fn. If little omega, Fn. Fn dominates Fn, Gn, yeah. It's Gn. Dominates Gn. Okay, analogy with real numbers like that, yeah. If big O, so Fn equal to big O Gn mean equal to F less than equal to G. If omega F greater than equal to G. If theta, because you are in between, yeah, in between what is C1, C1 or C2, this, yeah, C1 and C2 here. So this is C2, this is C1 Gn, so equal to. And if little o is less than F less than G, if little omega greater than G. Okay. And then we abuse of notation. Say Fn equal to big O Gn. Yeah, in the first case, this, yeah. Actually mean Fn is element of big O G N. So element, subset, element of subset of big O G N. It's not equal actually. It's only element or subset of. So it means it is Gn, yeah, Gn, Gn, Gn. So Fn is here. It's not the same, yeah. It's not the same, right? It's not the same. This subset, not the same. If the same, like mean here, right? So the same. This is the same, yeah, exactly the same. Fn equal to Gn. Okay, and this is quick math review. It's probably usually very like this for me. Okay, I believe in you guys. Okay. So called geometric progression because they told me, oh, like algebra, linear algebra, automata, theorem, and blah blah blah. Oh, discrete, and then oh, everybody already forget. And yeah, I believe in you. Okay, you just learn by yourself, yeah. Okay, geometric progression given an integer n0 and a real number 0 a, yeah, greater than 0 and not equal to 1. So sigma a power I from 0 until n equal to this. 1 plus A power 2 plus A power 3 and so on until A power n equal to what? 1 minus A power n plus 1 divided by 1 power minus A. Just remember your math in uh, senior high school, yeah, before we go to university. I also remember myself, yeah, in my room, I put so many formula for mathematics, physics, and so on, yeah, in order to have good preparation for national university entrance test. Yeah. And then this kind of, I think you guys already know, but for me, it's almost 30 years ago, yeah, more, yeah, more than 30 years ago. Yeah. I really believe in you, so you guys still remember this, yeah. So 1 minus A power n plus 1 divided by 1 minus A. Even in cram school, yeah, in cram school, like special lesson you took in order to be able to have a good preparation. They give you a trick, yeah, to solve the problem in national university entrance exam quickly solve the problem. And it does a geometric progression exhibit exponential growth. Yeah, here, yeah, you have this. Of course, there is an n there, yeah, n as the input size. Yeah, of course, input exponential growth, Yeah, yeah. So geometric progression, yeah, geometric. Another one is arithmetic progression. So this is have I in here. Here the I itself, sigma from I from 0 until n, I itself. So 1 plus 2 plus 3 blah blah, blah until n. Then is n power 2 plus n divided by 2. Okay. So will be used in many proving actually here, yeah. Okay. So you have this n over 2. This is 1, 2, 3 until n. This is linear, yeah. Linear should be what? This is this arithmetic, yeah. Should be this, yeah. So arithmetic this, yeah. Linear, yeah. 1, 2, 3, 4, something, yeah. And this is exponential, that geometric, yeah, here. This, right? So 1, 2, and then n over 2 is already woo, this, yeah. Okay. Be careful that exponential. Remember this sial, yeah. This unlucky, sial, exponential, unlucky. Be careful to avoid in the sense of running time, yeah. Running time, yeah. Time for running your algorithm, please possible to avoid this exponential, yeah. Okay. Then summation. The running time of insertion sort is determined by a nested loop. This running time of insertion sort for applying cut, determined by nested loop. This we have this, yeah, we have loop here. Yeah, this is actually loop, yeah. You have n and then you have another n, right? Nested loop correspond to summations. Ya, sigma j from 2 ya. J from 2 until n. Right? And then j minus 1. J minus 1. And become pico n square ya. Because it is your n and then that while itself also n. Ya. Of course then becomes square. Ya. N times n. Right? It means m square. Okay, we want to prove by induction. Yeah. So a bit we need to prove this. Usually in analysis PAA, we need to prove. We want to show that property P is true for all integers n greater than or equal to n0. Basis, yeah. Prove that P is true for n0. Yeah, right. By this insertion sort, yeah, we talk about insertion sort. Okay. Inductive step prove that if P is true for all k, such as this, yeah, k greater than or equal to n0, k less than or equal to n minus 1, then P is also true for n. Usually you are decided like this, yeah, you cut by k, yeah. And then you need to prove, yeah. Yeah. So if there is n0 and then k and n minus 1, yeah. Okay. Okay, yeah. Yes, you have a k, yeah, all of the k, yeah, until this, yeah, okay, because k from this, yeah, and then k until here, yeah, until n minus 1, n minus 1, and then it means n, yeah, this is if last one, yeah, is n minus 1 and then n in here, yeah. Then if this is true for all k, I mean all of this true, this of this true, then should be true also for n, this, yeah. Example this, yeah, Sn equal to sigma I from 0 to n. Yeah. Remember this, yeah? Was that arithmetic progression? I from 0 until n is geometric progression is sigma a over I from 0 to n. Yeah? So this arithmetic progression equal to this, yeah. Check this, yeah. N over 2 plus n divided by 2. Arithmetic progression and then yeah. And then you can throw that n, yeah. So n times n plus 1. It is the same, yeah. The same like n square plus n divided by 2 for n greater than or equal to 1. For the proof, want to prove this. Cobasis, yeah. If s equal to 1, I mean the it is from 0 actually, 0 until n, but if for 1, yeah. So sigma I 0 I from 0 until 1, then n from 1. Yeah, because remember this, if 0 divided by 2, of course 0. Yeah. Okay. So 1 times 2 divided by 2. Yeah. It's 1. Yeah. Yeah. And then inductive step, yeah, see. I mean, the basis one, yeah, it's easy. 0, we don't talk about this 0. Divide by anything, of course, 0, yeah. Okay, SK, yeah, SK, no SK. So 0 until K for I. Then, of course, you replace that n by K, yeah. It was n times n plus 1. So K plus K plus 1 divided by 2 for this. Remember, yeah, as we already did this. So K until this K1, blah, 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 until the last one, yeah. So it is n minus 1, and this is n. Okay. Yeah. Sn equal to this, yeah. From I plus n from 0 until n minus 1. So you have s n minus 1. I mean, plus n. We divide this is this, yeah, this in here, yeah. Then this n here, right? Okay. Then you can get n minus 1 times n minus 1 plus 1 divided by 2 plus n equal to n squared minus n plus 2n divided by 2, and then you got this. Then okay, you got inductive hypothesis correct. Right, so it's the same like n squared plus n divided by 2. And this, yeah, as you can see, correct, yeah. So that's the way how to do, yeah, how to do to prove, yeah, by induction, yeah. This usually we use for special case, and then we want to brought back into the more general case. Yeah, it's by induction, yeah, induction step or induction hypothesis. Induction by induction. Mm-hmm. Yeah, this proof by induction. Mm-hmm. Proof by induction consists of two cases. The first, the base case or basis, prove the statement for n equal to 0 without assuming any knowledge of other cases. The second case, the induction step. This case, because if it is 0, is very trivial, very trivial. Okay, then we move to actually 0 also should be okay because this. Okay, 0 divided by any this thing is 0 divided by anything, it becomes 0. Yeah, but anyway, it's okay. Yeah. No, I choose that basic one is S1. S1. Okay. Okay, now we learn about divide and conquer. Divide and conquer, DC. We talk about it, yeah, a bit in the last lecture. Divide and conquer method for algorithm design. So divide. Why we divide? If the input size is too large to deal with, too large, it's too big, yeah, too big to fit into memory. Too large to deal with in this straightforward manner. If we want to straightforward, I mean, right away we want to cut the solution, yeah, like that incremental or for like looping. But usually this is difficult in complicated problem. Oh, strike what is difficult? Okay, then divide it. Yeah. So divide the problem into two or more disjoint subproblem. This and become this and this. Then conquer. Use divide and conquer recursively to solve the subproblem. So actually, like kind of continue divide, yeah, until only one element, for instance. It's like we go to the basic one, the basis. Remember that inductive step, yeah, this basis until the very one item, yeah, the very item in only one, and then this we call it already got basis. Okay, so actually conquer is dividing all through, yeah, until the leaf if it is a tree, yeah. Then combine. So actually divide and conquer should be combined, yeah, but which is just divide and conquer. But the thing is, if you divide into until basis and then how to reconstruct your problem by combining. Actually, this is also very important, and it takes time, takes effort. So this there is a cost in here. There is a cost in here. So take the solution to the subproblem and merge. Remember that merge sort, yeah, merge sort. The solution into a solution for the original problem. Now we in merge sort algorithm, yeah. Divide if S has at least two elements, nothing needs to be done if S has 0 or one element. It is 0, of course it is sorted already. If only one, for instance, this or only one, like 10, of course this is already sorted. At least two elements then, yeah. Remove all the elements from S and put them into two sequences, S1 and S2, each containing about half of the element of S, i.e. S1 contains the first. This is a ceiling factor, yeah. Okay. And then another one is to contain the remaining floor. This is floor. This ceiling. This is floor element. Yeah. Okay. Okay. condition. This, yeah. Okay, just to remind you, yeah. Floor and ceiling function. This. Okay. For instance, this, yeah. Floor and ceiling. This, yeah. Ceiling, it means that, how to say that, edge on the bottom, yeah. Ceiling on the top, okay. Or this, yeah. So if 2, okay. Fractional, okay, nothing here. In 2.4 floor, it means you go down, become 2. Ceiling become 3 because you have the fraction. Yeah. Even 2.9, yeah. Floor, I mean just get rid any fraction floor, yeah. If ceiling function, just you promoted anything. If you have any fraction, just promote it, even though only 0.4. But if it is minus 2.7, this floor, and then become what to say, lowest, yeah. I mean minus 3. Ceiling, you are going up, you are promoted become minus 2, and so on, yeah. So this just remind you, yeah, and then you forget already. Okay, so this for flooring I mean to lowering, selling for promoting, yeah. This promoting, this is demoting. Okay. Okay, but anyway, this is something like this. Okay, this is left, this is right. Okay, conquer sort sequences S1 and S2 using merge sort. Then this combine, put back the elements into SY, merging the sorted sequences S1 and S2 into one sorted sequence. The algorithm in here, yeah. So you have EPR, so I have a array A, and then you got P, and this P, and then R. Okay, and then you divide, and there's a Q here. Okay, so Q is P plus R divided by 2. Okay, and then you go to A until, okay, method APQ, yeah, APQ. So this left one, and then Q plus 1. This is P and Q. This for the left, yeah. Then for the right, mean Q plus 1 until R, the right side. So this is this, this is this. Then merge PQR. And what is the algorithm here? The parameter is array A, and then the index P, index Q, index R. Take the smallest of the two topmost element of sequences APQ and AQ plus 1 R. The two, and then what? Topmost elements. Topmost element of sequences. And put into the resulting sequence. Repeat this until both sequences are empty. Copy the resulting sequence into APR. Topmost element. Okay, let's see this, yeah. Okay, you have array A, and then P, and then R, and then Q. Yeah. Okay, yeah. So this is the, how to say, unsorted. Then we want to sort these numbers. Yeah. Okay, yeah. So this, and then see this the left half, first half. Yeah, this left part. Okay, and then again going down. Again, first half. Again until 85. It is the base or the basis. Okay, and then because only one, yeah. Okay, then finish actually, and then okay for the, this is the left, yeah, part, and then the right part. Okay, then see what is the algorithm. The two topmost element, okay, 20. Then it is ascending, then, yeah, ascending from E to Z. Okay. 25, 24, then 24, 55. Okay, you go then. And then 63, 45. 63, 45. Okay, and then 45, swap. Yeah, this. Okay, you got that. Yeah. Then two topmost. Yeah. Then you just swap. Okay, 24, 45, 64, 55. Yeah. Okay. Then now the 17, 31, 96. And then you will cut this. Yeah. So cut A to C. Correct. Yeah, for sorting. Okay. Once again, you can check. Yeah. So I think very simple one. This is the smallest, yeah, smallest of the two topmost element. Topmost element. And it is ascending. Okay, ascending from from E C. Got this. Okay, yeah. And you grab the smallest of topmost. Again. Okay, smallest of topmost. Which one? 24, yeah, the smallest, yeah, between 85 and 24, it means 24, smallest of the two. Okay, correct, right? Yeah. Okay, now we have the recurrences. Yeah, recursive calls in algorithm can be described using recurrences. Recursive calls in our recursive function. Yeah, a recurrence in an equation. Recurrent is an equation or inequality. Equation mean equal to. Inequality mean you involving uh, the less than symbol or greater than. Yeah, can be this or this, can be this or this. Yeah, but they describe a function in terms of its value on smaller inputs. That is smaller inputs. Example method. You have Tn and then you have Tn equal to big theta 1. If n equal to 1. I mean method if only have let's say 2, yeah, of course, and then only one, how to say, one unit time, yeah, constant time, and then you got sorted. Yeah. Only only one. Yeah. Even if you have 0, of course it is already sorted. But if n greater than 1, how to do? You have Tn and then you have 2Tn over 2. See, there is T and there's 2Tn. But if n and become n over 2. And then plus Tn. Big theta n. Sorry, big theta n. That is the running time of method. You have recurrence. Okay. And how to, okay, solving recurrence. So we have this. Yeah. Okay. Okay, this is, yeah, itu. So before we recurrence, we just revisited the method, yeah. Okay, I mean it's easy to have this. Okay, yeah, to sort n numbers. Oh, where is that? Comment and to sort n numbers. If n equal to 1, of course done. Yeah, this if you see, yeah, this done. Yeah, if n equal to 1, of course done. This one need only one constant time, one unit time, one constant time, big theta 1. If everything about 1 like this, it means constant this. Yeah. In average big theta. Recursively sort to list of numbers. Yeah, this is floor function n over 2 and ceiling function n over 2 elements. Made to sort the list in big theta n time. And I mean in average big theta n. Yeah, yeah. So this is why actually this is for divide and conquer. DC, divide and conquer. This for what? Merging. I mean how to say combining. Yeah, this combining. Combine. Okay. So this, yeah, this is cost for combining or merging to the original problem. Yeah. Cost for combining. 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 Okay. Very difficult to write down by mouse. Yeah, see. So that's it. Yeah. That recursive, recurrent, divide and conquer, divide, conquer, combine. Yeah, divide, conquer, combine. Remember, actually, divide conquer is not only divide and conquer. Yeah, divide, yeah, divide, conquer, combine. Yeah. So this combine, yeah, it takes time here. This, yeah, this big data and yeah, this, okay, this. Okay. Okay. Strategy: break problem into similar or smaller sub problems. Then recursively solve sub problems, and then this combine solution to answer. We have input 1, 5 to blah 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 here, yeah. Then okay, split left, right. Okay, again still have left and right. Okay, again until the basic one or only one, 1 and 5, and then merge. Okay, 1 5 correct. Then for the other one 2 and 4, yeah, it is still correct. But when you merge, become 1 2 4 5. On the other hand, become also 2 3 6 6. Then these two merge become this. Yeah, this is the once again, yeah, we already know this. So smallest of the two topmost. Okay. Okay, now recurrences, yeah, because actually this solving recurrences. Okay, running time with using recurrences this equation. Yeah, again, is equal or inequality. Yeah, this or this, and then what this is cost of combining. Yeah, combining. This is for DC divide and conquer. I mean, divide and conquer. We have uh, three methods. Yeah, three methods, you guys. Substitution method, iteration or recursion tree method, and master method. Okay, by substitution method, we have guessing the solution. Guessing. Just predict guessing the solution. And then verifying the solution by induction. For iteration or recursion tree, it is much easy to see because you have a recursion tree. Expansion of the recurrence. You have recurrent design, and then you need to expand. And then drawing of the recursion tree because it's by picture. So it's okay. This diagram is much easier to see. Yeah, diagram. Yeah, diagram. For master method, you have templates of 4 different classes of recurrences. Okay. Okay. For instance, this substitution method. You solve this. It is not the same like method. Yeah. This method is Tn and then 2Tn over 2. This is Tn and then 4. It's divided by 4 then. 4Tn over 2 plus n. Then you guess that Tn equal to which one? For example, I guess big O n over 3. Usually the guess is also be if actually the actual here, yeah, you guess of course will be how to say worse than this. I mean the running time, because if you guess lower than, yeah, because become stupid. Yeah, usually our guess is how to say worse than what it should be. Yeah, I guess big O n over 3, i.e. that t of the form c n power 3. Okay. Then you assume tk equal less than equal to ck power 3. Yeah, for k less than equal to n power 2, n over 2. Yeah. Then you want to prove the n less than equal to cn power 3 by induction. Okay, Tn equal to this again, yeah, v 40 n over 2 plus n recurrence. And then it is equality. And then inequality less than equal to for c n over 2 power 3. Because you have this, yeah, then you just uh, substitute, yeah, this. Substitute this. Yeah, yeah, understand. Substitute this n over 2 because you guess this, yeah. Okay. Plus n by inductive hypothesis because you are higher, yeah, this is higher. Usually if we guess higher for running time, because the way is very stupid if you are actually the running time is less than it should be. Yeah. That's why uh, we guess usually a bit higher, yeah, that running time, yeah, a bit worse. Okay. Okay, and then by inductive hypothesis, okay, once again, you can equal to c power 2 n power 3 plus n. We simplify. Then we rearrange Cn over T minus this C over 2n power T minus n. Then you get less than Cn over Cn power T if C greater than or equal to 2n and greater than or equal to 1 satisfied. So thus Tn equal to pico n power 3. Okay. This is not factorial, this is only exclamation. Yeah, I got pico n power 3. Just remember, if you have a merge sort, and anyway you have actually big O n log n. O n log n. Okay. Okay. And then subtlety must choose C big enough to handle. Okay, Tn equal to big theta 1 for n greater than n0 for some n0. Okay. And then remember, we start from the higher, or also the longest running time, the longer running time. Okay. Then we want to make it tight. I mean, okay, we press down, to close the real running time, actually, Okay. It's by achieving the tighter bonds, tighter. Let's see this, the real one, this, the real one, real. Then we guess from there, okay, let's say n power 3, Then we wanna press this, to tighter bond, Try to show the n equal to big O n power 2. It was, we are sure that n power 3, and then for the this recurrency, you can check also for that example of this. Where is that? Yeah, this, inductive step, blah blah blah, something like this, the similar. Yeah. Assume not tk less than equal to ck power 2, not power 3 anymore. This is power 3 at worst, Okay. Okay, Tn equal to 40 n over 2 plus n. Okay, then inequality for C, you have that C n over 2 power 2 now. Because you need to substitute here, Then equal to Cn power 2 plus n. And less than equal to Cn power 2 for no choice of C should be greater than 0. If C 0, of course, it becomes stupid, Okay. This get rid, This get rid n, and then of course less than. Of course, you can get rid this n. Then if get rid n, then you need to throw here, then become less than. The problem, we could not rewrite equality Tn equal to Cn power 2 plus something positive as this Tn less than equal to Cn power 2. Because remember, this is something positive. It means you have, like this, You have, this is axis, You have something positive. There's a number. There is a value in that. Okay. So you cannot write away this. In order to show the inequality we wanted, sometimes to prove inductive step, try to strengthen your hypothesis. Strengthen. So like this, Tn less than equal to answer you want, then it is minus something positive. Something greater than 0 mean positive, Something positive. Okay. So see, this is plus, we have minus. We want to strengthening, your hypothesis. So corrected proof. So it was wrong, So now this correction, the corrected proof. This is the correct one. The idea is to strengthen the inductive hypothesis by subtracting lower order term. Okay, assume Tk less than equal to C1k over 2, then minus C2k for k less than n. Usually we have this, So I have a k, then k here. So this is k equal to n minus 1. This k should be less than n. So Tn equal to 40 n over 2 plus n. Okay. Then okay, you cannot write away, Then it should be minus C2 this, Not right away this, So then minus Okay, substitute ya. This power 2 and then minus C2 n over 2 plus n. So you add up this ya. You add up this something positive. Okay ya. Equal to C1 n power 2 minus 2 C2 n plus n. C1 n power 2 minus C2 n minus C2 n minus n. Then you can get rid this n ya. So C yeah this ya. C1 to C2. Yeah. So less than Cn1 n power 2 minus C2 n if C2 greater than equal to 1. Yeah, see like this, yeah, this equal to 1 because if C2 less than 1, yeah, it become not correct, yeah, right? This, okay. The basic idea, so this is the substitution method, yeah, okay, back to here. Yeah, well, a bit complicated, but to substitute, yeah, all the time you are just substitute what is your assumption and then substitute to that recurrent and that's it, yeah, and then you go. No, this is the first. Then for second one is iteration, or recursion tree method. The third one is master method. Yeah, okay, recursion iteration method is basic idea is to expand the recurrence and convert to a summation. For instance, this ftn n plus 3t and then this lower function n over 4. Then you expand this thing, yeah, you expand because recurrent, yeah, recursively. Okay, so see, yeah, then become n power 4, n over 4 plus 3t. Remember this 3t. Okay. And then it is power over 4 become over 16 then, yeah. And so on. 16 become 64. Okay. You expand the recurrence by this 3t, 3t, yeah, n over 4. And so on, yeah. Then you will count this, yeah, 3, then 9, then the 70, and so on, yeah. Plus 3, yeah. And divide by 3. I mean 3 times 3 then, yeah. Then 9. Yeah. 9 then times 3, 27, and so on, yeah. This. So you have this then n plus 3n over 4, 9n over 16, 27 over 64, and so on. Then actually you got this by observing the pattern 3 power 4 piece log n, yeah, t1. Then you got the summation. Way to summation. Of course, it's a bit complicated in mathematics, yeah. But only very love, yeah. And I think many of you doesn't like. The sigma I from 0 until this piece 4 piece log n minus 1, yeah, 3 over 4 and then power I plus is theta and big theta and then power 4 piece log 3, yeah. And then see you can calculate this, this become for n, this become for n plus big uh, this is little o n, yeah, because it's big theta n this and less than equal to big o n. Yeah, so actually, yeah, I think this is big O n. Yeah, or if it is 3t. Okay. The iterative method is often used to generate cases. Yeah. So it itself can solve our problem, yeah, for solve the recurrence. But this also can use the iteration method. This often used to generate cases for the substitution method. Remember, this is also quite difficult. This, yeah. Which one? Oh, n power n power 3 or n power, yeah, this n power maybe is 9 or with this one we don't know this, yeah. Should be higher than what it should be, but if too high and then it's a long way to get the correct answer. That's why this then to guess this substitution method, then you can use that iteration method. This generate guesses. Should know rules and have intuition for arithmetic and geometric theory. Oh, this is difficult, yeah. Because intuition, like somebody like Pak Ruli have. Yeah. my intuition about this mathematics is also very weak. Okay, yeah. And so know the rules. Yeah. Arithmetic and geometric series. And math can be messy and very hard. Focus on two parameters. The number of times the recurrent needs to be iterated to reach the boundary condition. Number of time, then boundary condition. And then the sum of the term arising from each level of the iteration process. Okay, this is the third one, yeah. The second one, but use the call recursion tree because it also can be this, yeah. Present, but we want to see like the view, the appearance, yeah, recursion tree. Okay, it's easy to see the diagram. Recursion tree is a convenient way. This part is convenient, very easy to see, to visualize. Visualize what happens when a recurrent is iterated. Okay, construction of recursion tree. Yeah, if we have ftn and then tn over 4 divided by 4, and then tn n over 2. So you have two component, and then another one n power. Yeah. Okay, so you have divide by 4 and then divide by half. Okay, so n power 2. Then if you continue, of course, and become 16, yeah, over 16 over 8, and so on. Yeah. So you can see here, yeah. So this n over n power 2. Then this 5 over 16 times n power 2, and add up this. Here all this, yeah, 25 over 256 n over 2. And so on, yeah. And then if you add up this, sum this big theta, n power 2. Okay. So easy to see, yeah. This is a geometry. Okay, another example, Tn is equal to T and n over 3 plus T to n over 3 plus n. Okay, this is n. And then n over 3. And then 2/3. So this is like 1/3. This is 2/3, yeah. Of course, if you add up this n, yeah. 1/3 plus 2/3, of course, add up n. And then if you continue, yeah, n over 9 to n over 9 and so on, you add up this all, yeah, plus n. Yeah. And then this, yeah. This, yeah, total is this, big O and log n. This usually happen for the best ever running time asymptotic analysis ever we have. So far is big O and like log n, big O and log. But maybe I don't know, maybe guys. Of course, I wish that someday you got your own inspiration, yeah, and then you can beat this big O and log n. You come up with algorithm, any algorithm that can beat this. I mean, better than this. Okay, we are very happy. Yeah. So this, how to say, the height, yeah, the height, the height, the height, height of the tree is 3 over 2 base log n. Because sometimes you have a log, yeah, the base is 10. If LG like this, I mean the base is 2. So this is the base is 2. This. Because remember you divide by 2, yeah, divide by 2. Okay. If divide by 10, yeah, of course you also can get 10 base, 10 base log. Okay. So 3 over 2 base log n. Easy to see the recursion tree. Okay, this is the number 3. Master method is a bit it's not difficult. You only have 3 template this master method. Okay, so what is the idea? So the idea is to solve a class of recurrence that have the form Tn equal to, there is A as constant, but it's like 2t or 3t or 4t, T and then n, and then this B over B plus Fn. See, if A greater than or equal to 1, and B should be greater than 1, yeah, because if B less than 1, become 0.9, it's not correct, yeah, I mean, we cannot see the pattern. So the requirement is A should be greater than or equal to 1 and B greater than 1. and f is asymptotically positive, not negative. This f is asymptotically positive. F, the function. And abstractly speaking, Tn is the runtime for an algorithm, and we know that this a subproblem. Yeah, remember if it is 2t, see back again here. Yeah. So t over this plus t. Okay, another one. Where is that? Is that short? Short. Oh, where is that short? This, yeah. Short example. This, yeah. See, met short. Yeah, this 2t. 2t. It means you have this and you are divided by two subproblem, yeah. This why you have Tn equal to 2Tn. 2Tn, let's say what kind of this over 2 or whatever, yeah. You have two subproblem. Okay. And here, this, yeah. So A, how many A subproblems of size n over b? What kind of sub? Because can be you divide by equally, yeah, equally. But sometimes not equally, like we did before, yeah. This is 1/3, this is 2/3, right? Where is that? This. Where is that? This, yeah, this, yeah. See, you divide by 2, but this subproblem is by third, yeah, 1/3 and 2/3, right? Because it can be half-half, right? Half-half. Okay, that's what I mean. This, yeah, what I mean. Yeah. So a subproblem. Remember this? We about pattern, guys. We are about pattern. A subproblem of size n over b are solved recursively. Each in time this t n over b. Remember a b. Yeah, this is a. This is b. Fn is the cost of dividing the problem and combining the result. Remember that divide and conquer d and c. Okay, number one d divide. Divide. Yeah, and then what? Conquer. Yeah. And then the test that combine, yeah, this combine, right? This combine. So this combine is this Fn, this, yeah, this, yeah. Combining this, so this. Fn is the cost of dividing the problem and combining the result. In math short, Tn equal to 2t n over 2. This right? If the subproblem is equal, yeah. So big, and then you divide equally. These two subproblem, and divide equally this b equally. And big theta n is the combining unit. If you have n input size and then yeah, here you need this for combining, the same like input size. Okay. Okay. So split problem into a parts at b base log n. So how many part? A part at b base log n levels, and they are a power b base log n equal to n power b base log a leaves, right? See if fn divide by how many? How many? This is how many part is A? A part is valid. This is how many part? If I say A equal to 3, mean 3 part, yeah. Then how many? How to say this is this size of NP, yeah, like 1/3 and something I said, yeah. And then this divide by how many B? Divide by how many B? Yeah, over P. Okay. Divide this all, yeah, Fn. Okay. This all, this of course A time F n over P, yeah, and so on, yeah. This. So if you add up this, become this big theta and b base log n. Big theta and b base log a. And the height itself, it is b base log n. It is correct, yeah, because you divide by how many? Half, like equally, or by, if it is equally, by 2, yeah, I mean 2 base, yeah, because divide by 2. equally. This it is equally divided by 2 and equally. But can be 1/3. It's by like b base log n. Okay. And this itself, it is n b base log a, right? And then total, this big data n b base log a plus this sigma a j fn over b power j from 0 until b base log n minus 1. Okay. Yeah, for this situation, I think the display is much easier to understand. Okay. Okay, now we have this. Then number of leaves, a power b base log n equal to this. You just kick this, it's easy. You just kick a to n. This. Okay. If you don't believe, you can prove by yourself. A power b base log n equal to n b base log a. Just you are swapping a to n. Iterating the recurrence, expanding the three yields. Iterating. Tn equal to fn, this at n over b, and then you are expanding. Then you will get this Tn equal to j from 0 until e base log n minus 1 a power j times fn over b power j plus this. So the first term is division or recombination cost total across all level of the tree. This is division or recombination cost total across all level of the tree. The second term is the cost of doing all n b base log a subproblem of set 1 total of all work pushed to leave. This. Okay. So this divide and conquer. This is like combining, combining. Okay. Okay, it is master method intuition. Even it is intuition. There are three common cases then, So this number 1, so 1, 2, and 3. Running time dominated by cost at leaf. It means when you are divide, and then this is very easy, but the running time mostly in here, Yeah. So like you are heavy duty in the leaf. Okay. And then the second one, running time evenly distributed throughout the tree. So the first one, this first one. So in this leaf, the second one, it is equally distributed, the running time. The third one, cost at root. So you are already running time in here, and then when going down to the leaf, it is much shorter. Dominated mean which one is running longer. So you spend your time more in there, dominated. Because you have three cases, three common cases, then you have to solve the recurrence. We need only to characterize the dominant term. Okay, dominant term. In each case, compare this Fn with this big O and power B base log A. Remember this. So this is the combining. This is the divide and conquer DC. Divide and then conquer. This combining. Only compare this. Only in each case compare this Fn or which one? Fn with this big O and B base log A. Okay, case number 1. Fn equal to big O and B base log A minus this epsilon for some constant epsilon greater than 0. Fn grows polynomially by factor n power epsilon slower than n power B base log A. So it is grows slower. This is grows slower, very slow, comparing to this combining, this combining. Okay. It means because this very slow, this here. This very slow comparing to this combining. It means then work dominated in the leaf then, this was very slow, right? So the work at the leaf level dominates. You see, this is very slow combining, So it means dominating here then, Okay. Summation of recursion tree level this big O and B base log A. Cost of all the leaf big theta and B base log A. Plus the overall cost because in leaf, yeah, dominate in here, and then we just count roughly here, yeah. This who care? I mean, this is very slow. I mean, very tiny, whiny, maybe some epsilon, yeah. That's why then we say that cost, the overall cost is this big theta and power b base log a. Okay. Case 2, yeah, this, yeah. Yeah. So Fn equal to big theta and b base log a, and you multiply log n. Okay. So it means they are the same. Yeah, yeah, yeah. Where is that? This, yeah. This equal. This equal. Yeah. Fn and b base log a are asymptotically the same. That's why the work distributed equally throughout the three. Level cost times number of levels. Okay. Okay, case 3. So the one is like this, yeah. So if it is on the leaf, yeah, on the leaf, work is dominated. So yeah, just big Fn equal to big O like this, yeah. You have minus epsilon. If the same, just log n. Remember, this is actually 2 base, yeah, log n. Then we write this Lg n. Okay, yeah, this. Okay. If case number 3, so plus, even plus, yeah. Big omega. This is big theta. Is, big theta for usually the average case, yeah, average case. This is big O for worst case. Okay, worst case, when yes equal, usually like okay, very slow, and then just right away suddenly, in the leaf one, whoa, you work very hard in here. It is theta average because yeah, you go. I mean the running time growing is equal with the combining. Yeah, this the combining. So this why this equal. Yeah, conversely, yeah, work at root dominate. So you when yeah you work very hard in here, and then when going down, and then the combining is very very less. This constant epsilon greater than 0. Inverse of case 1. This Fn grows polynomially faster than combining this, yeah, and power p base log a. That is why it goes very fast. Yeah, so this is work very hard and then gradually decreasing, yeah, until the leaf, but mostly in the root. Okay, also need a equality condition. There is axis C, yeah, less than 1, and n0 greater than 0, such that this F n over p less than equal to CFN for all n greater than n0. The work at the root dominates. This why Tn equal to big theta Fn. Because if dominate, yeah, where is that? This, yeah, yeah. Dominate means just focus on this. Combining is you can ignore it. This, yeah, can ignore it. This, yeah. Okay. This. Okay. Okay. And then master term summarize. You have some example. Yeah. This example, given a recurrence of the form this, the n equal to at n over p plus fn. Remember, this is combined this is define and convert dc. So if fn equal to, then this is this best case, this is average case, this is this is worst case. This is average case, this is best case. I like big O, yeah, big O and power b base log a minus epsilon, yeah, and then Tn equal to this, equal to that combining, yeah, here, because it heavily work in that leaf, yeah, this leaf. This is average, so big theta and b base log a, and then Tn you need to combine, yeah, not to combine, need to multiply. Remember this yeah, level cost, because it's distributed equally throughout the three. So level cost plus number of level. Let's say here, here, yeah. So need to multiply this, yeah, this and this. Yeah, okay, it's equally distributed, right? Okay, so by picture, it's much easier to understand. This and big theta, yeah, b base log a times log n. distributed equally ya here. For best case ya big omega ya, big omega n b base log a plus epsilon, and this Tn equal to only that Fn ya, this only this, because it is heavily on root. The Fn asymptotically increasing very fast before and decreasing to that. I mean that the running time is already very fast and then decreasing when in the leaf. Okay. So the master method cannot solve every recurrent of this form. Cannot solve every recurrent of this form. There is a gap between cases 1 and 2, as well as cases 2 and 3. So there is a gap, this and this between case 1 and 2, and as well case 2 and 3. How to solve this? So this strategy. Extract A, B, and Fn from a given recurrence. Determine N B base log A. And then compare Fn with this asymptotically. Yeah, combine. Then determine appropriate master theorem case and apply. For example, merge sort ya. The N and then 2T. Then divide by 2. Then this. So A equal to 2. Okay, this. B equal to 2. And N power B base log A equal to this. Yeah, this. Okay, just kick A and N. Then equal to N this. Yeah, N. See? N. Big theta N. Okay. Also Fn equal to, yes, this. So case 2. Case 2. Tn equal to big theta and B base log A log N equal to this. And N log N. So actually, this is equally distributed for short. Yeah. So we have very some N log N. This is as far as we know, it is the best. Yeah. N log N. Okay. Example, another one binary search. Yeah. We divide by 2. Yeah. And then for combining unit 1. Yeah. This, yeah, okay. A1, B2, yeah, this is. Then also case 2, big theta log N. Okay, another case 9, it is you divide by 9. Yeah, so A by 9. By 9, guys. Whoa. And each of them is by 3, by 3. This. Yeah. So A9, B3. Okay, this, and it is case 1. That means what? Case 1 means heavily in root, yeah. N equal to big theta N over 2. Okay. Another case, 3t N over 4, and then the Fn N log N. So I guess Fn equal N log N this, yeah. And then you have case 3, there's regularity condition. Okay, you have to read, yeah, by yourself if you don't have a time until you finish. Okay, regularity condition. So Tn equal to, okay, you read by yourself, yeah, until this big theta N log N. And okay, so regularity condition. Another case is 2t N over 2, but you have N log N. Okay, this is 2 like merge sort, but this. Okay. Okay. So neither case 3 or case 2. Yeah. Okay. Of course, it's different, yeah, different case. Another one, yeah, 40 N over 2, this Fn that combining N power 3. Yeah. This is 4, this is 2, and then N power 2. Okay. Case 3, this, yeah, power 2. But you need to check the regularity condition. Yeah. You check this, yeah. This is also the same. You have to check the regularity condition. Okay, yeah, regularity condition. Okay. Yeah, and then CF, and you have C equal to 3 over 4 less than 1. Yeah. Okay. Okay, that's it, yeah. Next time is quick sort and heap sort. This is kind of very theorem, yeah. It's like kind of theoretic, and you have to remember that math a bit, yeah. But it's not that difficult, yeah. You can you can consult to internet if you forget, yeah. Even sometimes also forget already, like I miss from 30, more than 30, almost 35 years ago, yeah. More than 30 years ago, so sometimes I also forget, yeah. Anyway, that's okay. I will stop a presentation today. Yeah. So inshallah for first assignment, yeah, there is no lecture, yeah. So only take your attendance, and then I will give you, I think, inshallah, clearer, yeah, about what you should do, yeah. Usually I ask my TA, yeah, hey, TA, you have any question, yeah, any question how to do for the assignment? If not, I just use the previous question, yeah. You can prepare by now, yeah. Inshallah tomorrow there's no lecture, only need to do, and as usual it is 1 week, yeah, open book, so you have plenty of time to do your assignment, yeah. Don't worry about this. Okay, guys, yeah, I think I will finish now, yeah. Thank you for your attention. I know it is not easy. Be patient, be with me, yeah. But remember, everything is open book examination, so don't worry, yeah. You can ask anybody, you can ask internet and so on, yeah. Okay, thank you so much for everything, guys. I will stop now. Keep healthy, be happy, yeah. Assalamualaikum, guys, and good afternoon. See you, guys. Thank you.
Thank you, sir.
Thank you. See
Thank
you,
you,
guys.
sir.
Thank you, sir.
Thank you so much,
Guys, see you,
sir.
guys. Thank you. Thank you, guys. See you. See you.